Okay, our final part for section 7.1 is dealing with Euler's method. So far we've discussed in dealing with solving differential equations, if we can use separation of variables, we can find an exact answer for a differential equation by doing the techniques that we've learned in solving for y. And then we have a straight equation, y equals, and we can use that to make whatever predictions that we need to. Now, we also discussed last time that if we can't find an answer using separable differential equations, using separation of variables technique, then we have no choice but to use a slope field. And the slope field is nice because it gives us a visual of what the y curve looks like. And if we have a visual of the y curve, then we can use it to make predictions as well. Now, keep in mind that it's not nearly as exact, and so therefore it would be nice if we can get an exact answer, which we can't in all cases. But if we can't, we can use a slope field. Now, thanks to Mr. Euler, we have another method that we can use to find an approximation to the solution curve. So again, still in the case where we can't find a answer for y by using separation of variables, but we can use what we call Euler's method instead, and we can get an approximation for whatever curve is in question. So let's see how that works. So here's the way it works in terms of the mechanics of it. The Euler's method is going to be used if we have something like, let's say, dy dx equals x plus y, and we'd have f of 2 equaling 0. So we have an initial condition, we have f of 2 equaling 0. And what it boils down to is we want to use Euler's method to approximate the value of f of 3 using increments of size 0.2. Alright? So here's what it boils down to. Before we get into the mechanics of it, this is what we're going to end up with when we're done. Okay, we already know that for our function, we know an initial condition. We know that it goes to the 0.20. Okay, ultimately, we want to know what's the y value at 3. And we're going to get there by finding an approximation for the y value at 2.2, at 2.4, 2.6, 2.8, and 3.0. Okay, we're going increments of 2. So bottom line is here, as we do this, we're going to be building a chart. And the actual question, the only thing we really care about is the end result here, which is what is the y value at x equals 3. But when we're done, we're going to have a chart here, which ultimately gives us points. And if we plot the points, guess what? We're going to have an equation for y looking at us in terms of a graphical standpoint. We won't have an equation for it, but we'll have a picture of this y curve. All right, so we'll deal with that in a few minutes. But bottom line here is when we use Euler's method, it's going to look exactly as follows. Okay, we're going to take our we're going to call it y1, if you will. That's going to be it's going to represent our next y value here. It's going to depend on the original y value, which we know, and then it's going to depend on the derivative. And when we write the derivative here, it's going to be the derivative of x0, y0, okay, times the change in x. Okay? So this is the general setup for Euler's method. All right, and what it boils down to in words is this: we're going to find a new y value by taking the old y value, and we're going to be adding the quantity derivative at the original point times the change in x. Okay, that's going to give us our approximation here. And what it boils down to is this really is just a linearization, and we're going to get to linearizations later in the class, but so we'll revisit that at one point. So the mechanics of it are this. So we're going to go y sub 0, which is our initial y value, that's 0. So we're going to have 0 for this time. We're going to have the derivative at our initial point, okay? And the derivative at our initial point is going to be 2, 0, because our derivative is x plus y. So that means that part's going to be 2, because it's 2 plus 0. And then the change in x is 0.2, okay? And the change in x isn't going to change throughout this problem because it's always going to be 0.2 as our change in x. So what does that tell us about our y value? 2 times 0.2 would be 0.4. And we ultimately will have that as our new y value. So again, filling in the blanks in our chart, we'd have the 0.2, 0.4. And then from there, we're going to get y2 by going with our y1 this time, plus f prime at x1, y1, delta x. So we're going to just iterate and continue to do the same cycle. And so our y2, our second approximation, is going to be the previous y value, which we found is 0.4, plus the derivative at 0.4, or at the derivative at this previous point, which is now this point. And if we put a 2.2 and a 0.4 in there, we're going to get 2.6. And then again, 0.2 as our x value. So if we calculate here, we will get our 0.4 plus 2.6 times 0.2. and we get 0.92. So now we're at 0.92 in terms of the y direction. Right? And then we're just going to continue this. We're going to go y3, we're going to go 0.92 plus, and then I'm going to take this point, and I'm going to put it into my derivative. 2.4 plus 0.92 would be 3.32 times 0.2. Calculate. So 0.92 plus 3.32 times 0.2, get 1.584. And then the fourth, which is going to be our next one, take that 1.584. We're going to put this point into our derivative, adding those two together. I get 2.6 plus 1.584, 4.184 times 0.2. So we'll multiply that by 0.2, and we'll add that to 1.584, and we'll get 2.4208. And then finally, our fifth one in this particular case. And as you can see, if we were to do this for a lot, it's going to take a while, but we generally don't have to do too many. So we'll still get our 2.4208 plus, and then if I add these two together, which is putting them into our derivative, we got 2.8 plus 2.4208, we get 5.2208 times 0.2. So if we go times 0.2, like that, and add that to 2.4208, and we get our answer, which is 3.46496. And we can round that to whatever decimal place is appropriate, and that would be our approximation using Euler's method. And again, not only do we get the approximation for the value of the function at 3, okay, with only the derivative in the initial condition, okay, but we also get this table of values, which ultimately it could be graphed, and we could see a picture of our curve. Okay. So what's nice is that this can be done by hand relatively simply. It just takes a little bit of time, because if we have to do five different guesses here, it's going to take that long. Most problems that we're going to do in our book are only going to ask for 2 or 3. On the AP test, which I'll show you an AP problem in a minute, they are only asking you usually for maybe 2 or 3 iterations at the most in solving a problem. But this is essentially the process. So that said, I'm going to show you a couple things too. We can also we also have a calculator program, because if we were to do this for 10 points, let's say, it would be pretty cumbersome. If we take our y equals and we put our x plus y in here, use your alpha y to get your y's in here, and then we use our program. We have an Euler table program, and the Euler table program asks us for the initial x, which is 2, the initial y is 0, and our step size is 0.2, and our number of points here, we want 5 points altogether to get to 3. And so let's see what happens. There's our 2, 0. This is how the program works. There's our 2.2, 0.4, just like we have in our chart. 0.92, 1.584. Looks like we're doing pretty good so far. Looks like we're doing very good. And ultimately we get the same answer with the calculator. So obviously the calculator is easier because it does all the arithmetic for you. But bottom line is that's how these numbers are being generated in that table. And the other nice program that we have here is an Euler graph program. And the Euler graph program, we'll do that same thing. Before we do that, though, I want to change the window from 0 to, or not from 0, but from 2 to 3. We'll go by 0.2 so we can see it. We can see what the y values are here. So if we go, let's say, -1 to 5, that should be sufficient. And if we do our Euler graph program at this point, it'll ask us again for the initials. So 2 is 0, 0.2 is step size. And you can see I'm kind of faintly here, but bottom line is here is we have, here's our points in question that are from this table, and if we can plot these points, as I said earlier, then we could draw a curve through them, and we can use that curve to make predictions. So even though we don't have an actual equation for y, okay, we have a picture of y, which is almost as good. So not quite as good because it's not exact, but it's pretty good. So, all right, break the program here, and we'll move on next. Whoops. Deal with that later. I want to show you a problem from the AP test from 2010. This was 2010. This is BC5. It's a BC problem because there are no Euler's method problems on the AB test. And we were given dy dx for this problem is 1 minus y. And it says the directions here are use Euler's method starting at x equals 1. By the way, the initial condition here is 1, 0. It says use Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 0. So knowing what I said earlier here with this chart situation, if we have 1, 0, and we want to approximate f of 0, okay, ultimately, if I'm going to only do 2 steps, then I need to have what here? Well, of course, that would have to be a half. So we'd have to go 1 to a half to 0 and figure out what these y values are. And notice that the one difference that we have this time as opposed to last time is that our x values were going left instead of right, but that really doesn't change anything. I'll show you how that does in just a minute. But bottom line here is we know that our y1 is going to be y0 plus f prime at x0, y0. And the reason that we write both variables in the derivative again is because sometimes the differential equation is written in terms of x and y. In this particular case, it's only y. So change in x here, of course. And so if we find our first iteration, we know that the first y value is 0. Okay, we know that the derivative at that point is 1 minus 0, which is 1. And then the change in x here would be a half. Now keep in mind that it would be negative a half, okay, because we're going left. So ultimately our answer then is just simply negative 1/2 or negative 0.5. So we got negative 1/2 here. And then from there, we only have one more to do, so this problem is easier than the last one that we did because we only have to do it twice instead of 5 times. But bottom line is we take that new y value that we just found, negative 0.5, and we're going to add to that the derivative at this point. Okay? And remember the derivative is this. So if we were to put, the only thing it depends on is y, so our previous y would be negative 1/2. So if we do 1 minus negative 1/2, we're going to get 3/2, positive. And then again, our change is negative 1/2. So we get negative 1/2 here. And over here we get negative 3/4. And so adding those together, 2/4 and 3/4 make negative 5/4. And so that would be our final y value because we only had to do 2 iterations of the same size. 0.5, 0.5 gets us from 1 to 0 with 2 iterations. And so the final product here is negative 5/4. So that right there is the answer. All right. And ultimately, the point breakdown on that from 2010 was 2 points for that. You got 2 points for showing the Euler's method work, or excuse me, 1 point for doing that part, and then 1 point for having the answer as well. So, okay, so you have some problems in your homework assignment today that deal with Euler's method, pretty much doing the same thing I did on these 2 problems.